Hey everyone, this is Ashwin here. In this video, we are going to see how to generate new anime faces using DCGAN. So GAN is a generative adversarial network. So this is a neural network model which generates new faces based on the training dataset. So here we have anime faces dataset. Usually this project will be done on like regular faces. I am a fan of anime, so I wanted to do it on animation images. So we have around 21,000 files of anime images, which is like 64 cross 64. As you can see, these are the samples of images. We could also see with the plot in the code later. So this images will be used as a training dataset, and with the help of GAN, we will be generating new anime faces based on the training images. So we are just training with anime faces. So the generator model also will be giving out anime faces only. I will also explain how GAN works throughout the code. So in the high level, we will be creating two models. One is generator, another one is discriminator. Generator will try to produce images like real images compared to this, and the discriminator will just tell you whether this image is a real one or a fake one. So these are the two models, and we'll be like training both the models, and finally we'll be using generator to produce new image. So that's the high level overview of this project. Let's create a new notebook and start with the project. So the notebook is loading. I'll just delete this cell, and let's name it as generate anime faces DCGAN. So this is like a basics of GAN. This is like a first model they have announced in the paper, and we will also see various types of GAN in the future videos. So it will be very cool, trust me. So this will be built on top of Keras and Tensorflow. So Keras Tensorflow, I think that's enough. Now, so if you click on this button, you will be getting all these parameters. So this is our data set. We will be getting the images from here, and this is the accelerator. When we are actually done with the coding, we will be using this GPU to train the model, as this is a neural network. And just turn on the internet just to download any other modules. Apart from that, other things is not necessary for now. So we could start with the project. Let me just increase the code cell a little. So I think this would be clear. Now let's import the modules. Import modules. Okay, the session is starting. It will take some time. First, we will import the base modules. Import OS, import numpy as np, import matplotlib dot pyplot as plot, import warnings, import from tqdm dot notebook, import tqdm. So these are the basic modules we'll be using, and apart from that, we will be importing a few TensorFlow modules. So from TensorFlow, import Keras. Apart from that, we will also import TensorFlow as TF, and from TensorFlow dot Keras dot preprocessing preprocessing dot image. So we have to like pre-process some of the images. So import load image and image to array, sorry, array to image. Yeah, I think this is done. And we also need to import optimizer loss and necessary models for creating the models. So from tensorflow dot keras dot models import sequential and model. So this is one, and from tensorflow dot keras import layers, and from tensorflow dot keras dot optimizer import Adam. So if you don't know how to set up the optimizer like SGD or anything, just always go with Adam. This is like a best optimizer for the base case. If you are like fine tune the model more and play around with the parameters, means you can go for SGD with momentum. And from tensorflow dot keras loss import binary cross entropy. Okay, finally warnings dot filter warnings. We'll just ignore all the warnings. Let's run this. So we have imported all the necessary modules, and load the files. We'll just load the images. Let's create some code as well. Okay, now we have to create the base directory. So base directory, we will just specify the path. You can get the path here. So data, paste it, and data. Okay, so this is the path of the base directory. And after this we will create a list containing all the images. I will call it as image paths as a list, and for image in os dot list thereof base directory. Now image path equals os dot path dot join of base directory and the image. Okay, this will just iterate the directory, so it will contain like all the images. So this will contain like the image name. Maybe I can also say it as image name, and finally I will just append this to the image path list dot append image path. Okay, run this. So it will contain like all the images. So when I tried this project, I found out like one file have like another folder or something, so we have to remove that. So image paths dot remove of just have the base directory data and data. So this will just remove that element. You can also see the image paths we have got. So these are the images with the complete path, and I will also get the length of image paths, and after removing this we'll be getting, see, we have deleted that data successfully. So we have 21,551 images, which has been mentioned in the description of the dataset. So that's done. We could delete this. Okay, Now let's visualize the images. Visualize the image dataset. Okay. To display grid of images. So this will be remove unnecessary file. Load all the complete image paths to the list. Okay. Now let's plot it. So plot dot figure of fixed size. Fixed size equals, I can have around 20 cross 20. We could also adjust the size later based on the image plot it is showing. And I will temporarily take few images. So temp images equals image paths of 49. So I'm gonna display a plot of 7 cross 7. I will tell it in the bracket 7 cross 7. So 7 cross 7 is 49. So 49 images I'm just taking, and I will also initialize index equals 1. Now for image path in temp images, now plot dot subplot of we have to define the grid 7 cross 7 and the index. So here the index is starting from 1. Now load the image. So image equals load image and the image path. So this module is imported using Keras image path and convert to numpy array. Now image equals np dot array image. Show the image. Plot dot imshow of image, and we will just set out few things. Plot dot axis of, so it won't display some units on the axis on like x and y, and we will also increment the index. Increment the index for next image. So index plus equals 1. Let's run this. Okay, now you can clearly see the faces of enemy characters. I have displayed 7 cross 7. Okay, some of them are not faces. We cannot get these images, so it is fine. So overall all of them are like faces of an enemy character, so this is fine. And by the way, I watched like most of the anime series, anyone you name it. So my first anime is like Death Note. If you guys also watch anime, mention that first anime you watched in the comments. Maybe I'll just create another video based on this anime characters, and we will just create some projects on that. Let's see. Okay, now we have done the visualization. We will go to the next step. So now we have to pre-process the images. Pre-process image. Okay. Now train images equals, I am just using list comprehension. So np of array, just leave it for now. So for path in tqdm of image path, so I'm just iterating over the image path list, and I'm loading the image and converting to numpy array. Loading the image with the path, and I'm converting to numpy array. load the image and convert to numpy array. Okay, once this is done, I'll just convert everything to numpy array. So train images equals np dot array of train images. Run this. Yeah, now it is working. Okay, so it could take a while for this to load. In the meantime, we will just check the shape at the end. So train images dot shape. So this will give us the overall shape. I think anyway we will be running all these with the GPU machine. It is fine, we will just keep on running. We are not like losing our money. So after the shape, we will just reshape it once again. So instead of this, we will just take one image and get the shape, and after that train images equals train images dot reshape of train images dot shape of 0. So this will give the length of the train images, that is number of images in the whole dataset, and we have to reshape it to 64 cross 64 comma 3. So if you have like different resolution of images, if you want to train it, means just mention the resolution here. So this is the width and height, and this is the number of channels. So this is a RGB image, that's why we have 3 channels. If we have grayscale, means we will just mention it as 1, and as type of float 32. So this will just reshape the numpy array, and after that reshape the array, normalize the images. So we have to normalize the images in the range of -1 to 1. So usually when we do normalization, it will be in the range of 0 to 1. So we will just divide it by 255. But in the generator model, at the end, the activation layer is tan h. So it will give values in the range of -1 to 1. So we have to change the image output accordingly. So train images equals train images minus 127.5 divided by 127.5. So first we are negating it by 127.5. So if the pixel values are in the range of 0 to 255, so this will just make it in the range of -127.5 to +127.5, and we are dividing it by 127.5, so it will convert this in the range of like -1 to 1. So we will also check one example after this. So train images of 0. So we will just see some values. So after this, we have to create the generator and discriminator models. Create generator and discriminator. I will also explain why we need two models and what is the function of each model. So we will check that after running these code snippets as well. In the meantime, I'll just initialize few things. Latent dimension for random noise. So I will call it as latent dimension. So I'm currently setting it as 100. So this is like a 100 dimension. So the random noise initially we are going to generate based on this dimension only. So if you reduce it to like 10 means it will the variety of images it will generate will be reduced, and if you increase the latent dimension, let's say 150 or something like that, means it will give variety of images. So based on the latent dimension, the image results we are going to produce will be differing. So this is one important parameter. And weight initialization, so this will be used as per the paper. So weight initializer, so this will be used in the model. Okay, this is done. Let's see the shape. Okay, so 64 cross 64 and 3 channels. Let's do this as well. Run this. Okay, now normalize. So now you can see some of the ranges. You can see my -1, and you can also see some values in the positive side like 0.5, 0.45, and there will be somewhere there will be 1. So this is like a sample of values after normalization. Okay, now we will resume. Now the weight init equals tf dot keras dot initializers. I have imported keras as well. Initializers, let me just check. Okay, I given some suggestion. Initializers dot random normal. I will set the mean as 0.0 and standard deviation will be 0.02. So these are the parameters that is specified in the paper, and the number of channels for the image, number of channels of the image. So channels equals 3. So if you are using grayscale, for grayscale keep it as 1. Okay, now that is done. Let's create the generator. Generator model. Now let's create the generator, and after that I will explain how the model works. So model equals anyway we will be starting with sequential. So I will specify the name as generator because we will be having like 2 models. And first we will have 1D random noise, model dot add of layers dot dense. You can also specifically import these layers, but I'll just call it from the layers module itself. So I will have 8 multiplies 512. So this is the random noise we are generating, and I will specify the input dimension. Input, okay, it's not showing. Input dimension equals latent dimension. So this is the input, like the 100 dimension, and from that input it will just go with this number of units, and after this, usually after each layer we will be having batch normalization and ReLU. So let's add that. Model dot add of layers dot batch normalization, and followed by activation layer. So layers dot ReLU. Okay, So this will be the convention for this model. So this is the first layer, and second layer will be converting this one dimension to three dimension because we have like three channels. Convert 1D to 3D. Now model dot add of layers dot reshape of we have to specify the target shape, that will be 8, 8, 512. So initially it will be like 8 cross 8, and in the progression of the layers we will be keep on upsampling the image to get the final resolution of 64 bar 64. Okay, now the first thing is done. Let's add more layers. So upsample to 16 cross 16. Now here we are going to use convolutional 2D transpose followed by batch normalization and ReLU. So model dot add of layers dot con 2D transpose of 256. We will have a kernel of 4 cross 4, so it will be used for upsampling, and strides equals 2, 2 followed by padding equals same, and lastly kernel initializer equals weight init. So this is the weight init we have specified. Usually it will be like random weights, but for here we will be having the weights in the range of minus 0.02 to plus 0.02. So this is the con 2D, and after that we will just copy this 2. So this is another layer. We will just keep on upsampling the image or input until we reach the final result. So just copy this and paste it 2 times. So this will be 32 and 32. So this will be 128. 4 cross 4, everything remains the same, and this will be 64, and here it will be 64 cross 64, and again everything remains the same. So once we have reached 64 cross 64, we will have the final con 2D with the activation layer of TANH. So model dot add of layers dot con 2D of the number of channels we have specified, right? So channels, comma 4 cross 4, and padding it will remain the same, and activation, so this will be TANH. Remember, we have normalized the images in the range of -1 to +1. So this TANH will give you the results in the range of -1 to +1. So this is the whole generator model. So initially it will just create random noise based on this units, and we are just reshaping that into like 1 dimensional to 3 dimensional, and from there we are keep on upsampling using con 2D, and when we reach 64 cross 64, which is the target size, we will use the final convolutional layer with the activation of TANH. So this will give us the final image. So I will name the model as generator. So I'll just assign a new name and generator dot summary. Okay, let's run this. Okay, now we have successfully created the generator model, and the parameters you have to change it according to the image size you are using. If you are using like odd number of images, means you can change the kernel size as well. maybe I could create a separate video on how to create a convolutional neural network based on the images, but usually just go with some paper usually that have like a very good configuration of the whole network. Now this is done. Let's create discriminator model. Discriminator model. I already said generator model is used to generate images from random noise. Discriminator model is used to classify images whether it is real or fake. Maybe I'll just have the explanation as well. Generator model will create new images from the training, similar to training data, from random noise. Okay, now for the discriminator model will classify the image from the generator to check whether it is real or fake images. So why the discriminator have to do this? So based on the discriminator only we are training the generator. So the objective here is we have to train the generator model until we fool the discriminator. So when we create the new image from the generator, the discriminator should accept that new image as a real image. So until that we will just keep on training these models, and we will also periodically check the results, because usually from other classes we will usually have some validation data, and we will usually have some classes, and we will keep on checking the scores. But here we will just have losses, and we have to check the quality by seeing the output from the generator by using our eyes. So there are other metrics that we could use, but I could cover that in the future videos of GAN. But for now we will just train these two models and see the output directly, and infer the images. Now let's create the discriminator model. Again, model equals sequential of name equals discriminator. Here we will just specify the input shape, so that will be 64 and 3, because here we will just pass it as an image. It's like a regular convolutional neural network, and we will have alpha equals 0.2. So this is used in leaky ReLU. So that is a activation layer that is used for discriminator model. Now let's create some layers. Create con layers. Now model dot add of layers dot con 2D. So here we are just using con 2D. We are not going to do any transpose. So here we will be downsampling the images. So 64, I will have kernel 4 cross 4, and strides will be 2, 2. Okay, I missed one brackets. After stride, padding is there. Padding equals same, and lastly we will pass the input shape only for the first layer. Input shape equals input shape. Now here again we will be having batch normalization. Model dot add layers dot batch normalization. And finally we will have the activation layer, layers dot leaky relu and alpha equals alpha. So this is the first layer, and we will keep on downsampling the images. So this will be 128 and this will be 128, and finally I will just flatten everything. Model dot add layers dot flatten, add a dropout layer, layers dot dropout with 0.3. You can set the range of like 0.3 or 0.4, and we also should not train a good discriminator, because if you are training like a strict discriminator, means the generator won't learn anything. So you have to create like a lenient discriminator. So you can read more about how to create this kind of discriminator for effectively train the generator model. And finally we will have the output class. So output class model dot add of layers dot dense of 1, activation will be sigmoid, activation sigmoid. So this is the discriminator model. So it will just classify whether it is whether the image from the generator is real or fake image. Now I will change the name, discriminator. It's like a terminator, but yeah, discriminator, and discriminator dot summary. Let's run this. Okay, everything seems to be good. Now after this will be like an important step, and it will be like a long step for you guys. So create DCGAN. So here we will be combining both generator and discriminator, and we will be overriding the Keras model class. So we have to like train both the models at the same time and update the weights with customized loss functions. So I'll be adding everything inside a class, overriding a few things. Let's go into this in detail. Okay, class DCGAN, and we will be having Keras model. Okay, in the initialization we will have the basic details. So def, so this is the constructor, self generator discriminator. I hope I spell everything correctly. And latent dimension. So we have to call the super. Don't worry about these things. These are like basic initialization. You just focus on the upcoming parts. So these are like initializations we have to do. Self dot generator equals generator, self dot discriminator. So these are the models we have created before. We will just pass it through this class, and discriminator self dot latent dimension, and finally we will be having loss metrics for generator and discriminator. Self dot g loss metric equals Keras dot metrics dot mean. Name will be GLoss. We have to do the same for discriminator. Self dot d loss metric equals Keras dot metrics dot main. Name will be d loss. Okay, these are the initializations. After that we will have metrics. So it's like a override at property def metrics of self. Here we will return those two metrics, discriminator and generator. So self dot g loss metric, self dot d loss metric. So both metrics will be returned while training the model, and we will usually do the model dot compile, right, with the optimizer and the loss function. We have to override that function as well. Def compile self. We have to pass the parameters. So G optimizer and D optimizer loss function. So super DCGAN comma self dot compile self dot D optimizer equals, okay, first we will have the G. So G optimizer self dot D optimizer okay, and self dot loss function okay. Now the compilation is also done. So after this will be the main part, which is the training steps. So def train step of self comma real images. So this will be like a train data we will be passing to the model. So first we will get the batch size, get batch size from the data. So batch size equals tf dot shape of real images of 0. So this will give you the number of images that is present in the batch. So that will give the batch size. Generate random noise. As I said before, we have to generate a random noise. So I will call it as random noise equals tf dot random dot normal. We have to pass the shape. So shape equals, we have to pass the batch size. Why it's not suggesting? Okay, batch size and the latent dimension. So this will generate the random floating point values. So this will be like any starting point. So based on the batch size, so it will create random noise for let's say batch size is 32, means 32 images, and the length will be 100. So because we have initialized latent dimension as 100. So after creating this, we will train the discriminator first. Train the discriminator with real and fake images. So real images, it will be label 1 and fake images will be label 0. Okay. Now with tf dot gradient tape as tape, compute loss on real image. So pred real equals self dot discriminator of real images training equals true. So this is the training step. So I'm just passing the images directly to the discriminator, and I'm getting the predictions from it, and based on that we will compute the losses. Generate real image labels. We didn't label the images yet, so we are going to do it now. For real images, we will label it as 1. So real labels equals tf dot ones of batch size. It will just create tensors with the number of batch size and 1. So it will just generate ones with this dimensions. So this is real labels, and there is one more technique called one-sided label smoothing. I will apply it here. So real labels equals plus equals 0.5 multiplies by tf dot random dot uniform of tf dot shape of real labels. It's very slow, I guess. So real labels. So this will generate values in the range of 0 to 1 with the shape of the real labels. So it will almost equal to the batch size, and we are just multiplying it by 0.05 to apply the label smoothing. So this is one of the technique that will improve the model, and finally we will compute loss on the real images. So d loss real equals self dot loss function of real labels and prediction real. Okay, now this is done for real images. Let's do the same for fake images. Compute loss on fake images. So to get fake images, we will be getting the output from the generator. So fake images equals self dot generator of the random noise we have generated before. Now we will get prediction fake equals again self dot discriminator of fake images, and the same argument as it is, training equals true, and we will generate fake labels, generate fake labels. So fake labels equals tf dot zeros. As I said, for fake it is zeros with the same batch size and 1, and we don't need to do any kind of smoothing here. Finally, we will compute the loss fake equals self dot loss function of fake labels and pred fake. Okay, this will compute the loss function for real images and fake images. Finally, total discriminator loss equals dloss equals dloss real plus dloss fake divided by 2. So this will be the total loss of the discriminator. So usually when you are training the conventional layer, you don't do all these things. You just specify binary cross entropy or some loss function and it will automatically do all these things. But here we have to customize few things because the two models are kind of interconnected with each other and both of them needs to be trained at the same time. Now we have to compute the gradients. Compute discriminator gradients equals tape dot gradient of dloss. We have computed the loss and currently we are just finding the gradients. So self dot discriminator dot trainable. Okay, it's not suggesting any. So trainable variables. So this is common for all the models. If some layers are freezed, means we won't be updating the gradients to that variables. So we will just calculate the gradients for the trainable variables and we will update the gradients. So this is the classic deep learning framework and we are just going step by step. So if you completed this, means you can like work on any complex model. Now let's update it. D optimizer dot apply. It's not suggesting anything. Apply gradients of zip comma grads comma self dot. I'll just copy the whole thing. I'll just update the gradients to the trainable variables. Okay, now the discriminator portion is done. Now let's train the generator. Train the generator model. Okay. So here we will just create the labels. tf dot once, again the batch size comma 1. We have to train the generator to create and to confuse the discriminator that the generated images are like real images. So for that only we are creating the labels with tf dot gradient tape as tape. First we will get the fake images from the generator. Self dot generator I will pass the random noise that was generated before, and here also training is true, and I will get labels from the discriminator. Generate fake images from generator, and here generate classify images as real or fake. So self dot discriminator, I'll just pass the fake images that we have generated from the generator. Here training equals true, and finally we will get the loss function. Compute loss. So G loss equals self dot loss function of labels comma predfig. So from the labels we have created, it will just get the loss function here. So as I said, generator wants discriminator to think that fake images are real. So here we don't update the weights on the discriminator, we will just update it on the generator. So compute gradients equals tape dot gradient of G loss of self dot generator dot trainable variables. Now we will update the gradients. It's a lot of typing for this project. So self dot G optimizer dot apply gradients, and again zip of, okay, this will be gradients, and here also gradients, self dot generator dot trainable variables. Okay, now we have updated the gradients for the generator. Now finally we will update the states. Update states for both models. Self dot d loss metric dot update state d loss, and self dot G loss metric dot update state of G loss. So both the losses we already calculated before, and finally we will return d loss self dot d loss metric dot result, and G loss self dot G loss metric dot result. Okay, that's pretty much it for the DCGAN class. Gosh, it's like a big class we have created. We have to like modify so many things because of this GAN. Even in future projects, I think we have to do a lot of this. Maybe we could reuse some of this instead of creating everything from scratch. So this is the first video I want you guys to understand what's happening. Maybe I'll just go through the function again. So initially we are just in the constructor we are initializing everything like the models and the metrics, and this will be called when we are calling like model.compile with the optimizer and the loss function. So the important part is the training step. First we are getting the batch size based on the batch of images we are passing, and we are generating random noise from the latent dimension. So here it is like 100. First we are training the discriminator. First I'm computing loss for the real images. So with the real images we are just getting the prediction, and we are just created some real labels, which is 1 with the help of tf.ones, and I have applied label smoothing here. So this will give us some improvement, and we are computing the loss with real labels and the prediction of real. And we are doing the same for fake images. The labels will be 0, and we don't do label smoothing here because it doesn't matter. And we are calculating the total discriminator loss from both the losses we have got. And finally we are upgrading the gradients for the discriminator. And in the second part we are training the generator. So we are training the generator to make the discriminator to think that the fake images are real. So we have to train the generator until the fake images will be considered as real by the discriminator model. So first we are getting the fake images from the generator with the random noise we have generated before here, and we are classifying the images whether it is fake or not based on the labels. And finally we are getting the loss function. So, and again based on the loss we are computing the gradients, and we are updating the generator model, and finally we are updating the loss matrix and returning it. So this is the whole workflow of how the training is done. If you already seen PyTorch model creation, means all the steps we will be doing like step by step, like updating the gradients and going back and calculating the gradients and everything. So now this is done. We almost reached like 70 to 75% of the project completion. We just need to like create few more things. In the meantime, we will enable the accelerator GPU. So turn on GPU. So okay, I have to run some cells. I will just run all. Okay, I think we don't need the markdown. And after this again, as I said, for each epoch or some epochs we have to print or plot some images. Plot some images means we have to plot the prediction of generated image just to see how the quality is improving. So we will create another class DCGAN monitor Keras dot callbacks dot callback. So it is running, so I have to type it. Now again we have to initialize the constructor init self. So we will pass num images equals, I will set it as like 4 by default, and latent dimension will be 100. These are like default parameters. We will initialize the same self dot num images equals num images. Now self dot latent dimension equals latent dimension. Again, we have to like create a random noise for generating images. Create random noise for generating images. So self dot noise equals tf dot random dot normal of how many images we are going to create. Maybe I will just say 5 cross 5. 5 cross 5 means total will be 25 and the latent dimension. So this is the initialization and def on epoch end. So after each epoch we have to do this on epoch end of self comma epoch and logs equals none. So you can also use this for like every epoch. So for now I'll just say epoch modulus 2. For every 2 epochs I will display the image, or we can just go as it is. I will say g image equals self dot model dot generator of self dot noise. So this is the input, and g image equals g image multiplies 127.5. We are just denormalizing the image. As I said, the result will be in the range of -1 to +1. So we are just multiplying it by 127.5 and we are adding 127.5. So this will just make the images in the range of 0 to 255. I will also say denormalize the image and generate the image from noise. After that I'll just convert to numpy. So g image dot numpy. Now fig equals plot dot figure fig size equals, I will say 8,8. I think that is reasonable. And for I in range of self dot num images. So based on the number of images we will just iterate this. So plot dot subplot, we will quickly type this because we already done this. 5 cross 5 and I plus 1, this will be the index. Image equals array to image. So we already loaded this function as well. Array to image g image of I and plot dot im show of image, and we have to set the axis to off and finally plot dot show. So this will just display the image, and if you want to save the image I will just leave the snippet in the comment. You can uncomment it if you want to save the image. So save fig equals epoch underscore colon 03d dot png dot format of epoch. So this will just save the image based on the epoch number, and that's pretty much it. One last function is pending, def on train end self and logs equals none. We will just save the model. So self dot model dot generator dot save generator dot h5. So you can reuse the model later for generating new anime faces. I think all the cells have run successfully. We'll also run this. Now let's quickly initialize the model. So DCGAN equals DCGAN of, first we will have to pass the generator discriminator latent dimension equals latent dimension. You can also pass with the parameters. So sometimes if you just confuse between generator and discriminator, you will get an error. So I'll just pass with the parameter, run this. Let's compile the model. I will also set the learning rates. So DLR equals 0.001 and GLR equals 0.0003. I'm just setting discriminator with less learning rate because if we quickly train the discriminator, the generator won't learn because the discriminator will learn everything, and it will just suppress the generator to train better. So always train the generator faster and train the discriminator much slower. Now DCGAN dot compile of, so G optimizer equals Adam of learning rate equals G learning rate and beta 1 equals 0.5. I'll just do the same for D optimizer equals Adam, and this will be DLR, and finally we will pass the last function equals binary cross entropy. Okay, so just this is a function. Okay, we have compiled the model. Now let's mention an epochs equals, I will have it as 50. Now let's train the model. So DCGAN dot fit, I already have like train images. Epochs equals n epochs, callbacks equals DCGAN monitor. We have created that before. DCGAN monitor of, we can just leave it as it is because we have specified num images as 4, but yeah, we could specify it as 25. So you can also pass some parameters, like if you want to modify the images. I'll just leave it as it is. Let's do the training. I hope this works without any errors. Okay. Yeah, now the training starts and I can see the loss is getting updated here. Okay, array image is not defined. this is array2 image. See, sometimes this will happen. Okay, again I will compile everything. I don't know how many issues will come. I will also check everything is like have set it correctly. So we have come a long way to creating like multiple models and combining all the multiple models to train it as a one. And yeah, this is great. Let's see whether it is generating something. Okay, now it's generating something. So these are like a random noise. So without training anything, this is what you get. It's like some kind of what you say, some kind of like bacteria or something. Over the period of time, we will see some improvement. So we have to like wait for a while and see. So I've been training this for a while, and the loss has been like exploding. So the discriminator loss is going like minus 300, and generator loss is also going like 240. Still the images are like producing, and it is improved compared to the start we have seen. So this is the start. So I think this is due to, in the generator we have added batch normalization. Just comment this part alone, and we'll just rerun the model after doing the commenting part. So after this the model is giving like a loss in positive only, so the training speed also got increased. So let's rerun this after doing the commentation. Just comment this part alone. So I have started running all the cells. So let's wait for some time, and we'll see how it is getting updated. We will compare the images from the like first epoch to the last epoch for general comparison, and how the results are improving over the period of time. So we have been training this for a while. So I have trained the model for 50 epochs, and this is the first generated image from the model. As you can see, it's just some random noise, and it didn't predict any faces at all. So this is the first phase. This is how you feed the input. This is almost similar to the input we are giving, and progressively on each epoch it's keep on improving. So here we could see some faces, and over the period it is keep on improving. So I can see the eyes are getting improved, and the facial structure is also getting improvised. And even in the 11th epoch itself we are getting some good faces overall. And when we reach like more epochs, so now you can clearly see the difference. So we are not getting some distorted pixels in the image. Everything is smooth, and we can see the whole face. So this one is good, but this one is like a Tokyo Ghoul character. So yeah, this one is also good. One red eye and one blue eye. And let's go down further. Now you can see at 31st epoch we are getting some different characters. So for each generated image we are getting like a variety of characters. That's why we had set the latent dimension as 100. If we set it as like 10 means the variety will be like less, and if you set it like 130 or 150, you will be getting more variety in the images. And the clarity of the images was also getting increased over the epochs. Let's go to the last few images. So here you can see the hair strands of the image. That is really great. And we almost reached the final one. So this picture and all, it is really good. This picture and this one and all, the facial structure is really good. And this is the final image. And as you can see, we can like train further, but this is the maximum we could get. Like for the past 20 epochs we are getting some pretty good results from DCGAN. And if you try out other GANs in the future, means it will definitely improve this quality of the image we are getting. So we will definitely see that later. And as you can see, just because of that one change in the model, we have like improved the training quality of the model. So make sure you set like right parameters for everything in order to get better results. Even if you make like a slight mistake, it will give you some low quality model. Now that's pretty much it, guys. If you want to generate images from the scratch, we already done that part. So this is the generation. So I can also like copy this, and we will get something from this. So maybe I'll just copy this whole function and modify it in a new cell. So I will call this as generate new image, new anime image. So we will just paste this. Now we already have these things. I'll just remove these things. I need some noise. I'll just create only one image with the latent dimension of 100. Now I will generate image from the noise. So this will give us the image, and here I'll also delete this. So array to image, this will be 0, and yeah, you could save the plots as well. Let's run this. Okay, I think I have used self. This will be DCGAN dot generator. Okay, this self is also we have to remove. Okay, now you can clearly see the image. So this is the image. Each time if you run this, means it will give you new images, so you can see the quality of the images as well. So let's just keep on trying until we get some good image. So this is like somewhat good for 64 cross 64. If you just adjust the figure size, it will be much clear for you. Maybe I'll just take that snippet as well. So this is the plot. I'll just update it here. I will have 3 or 2 cross 2. Okay, now we are getting like a smaller image, and we can clearly see the image as well without any distortion. Let's have this one. Okay, yeah, I think this is the ideal size. Let's run this for a few times and see whether we are getting some. Yeah, we got some good faces before, and now we are getting some faces, but it's like somewhat messed up. So this I think this face is somewhat good. We have like blonde hair, red and blue eyes with the face, so this is good. You can also like generate some random numbers, or you can specify some numbers in this dimension, and you can feed that as an input as well. So that's pretty much it, guys. So this is how we could generate our faces from DCGAN. So we will be working out a few more GAN models with other datasets as well. If you want to continue with animation datasets, please let me know in the comments. Apart from that, if you have any queries, just leave a comment below. I will definitely answer that. That's pretty much it, guys. If you like this video, hit the like button and don't forget to subscribe the channel for more videos like this. See you guys in the next video.